You know when you're streaming a movie on your phone or you're on a video call while walking around the house and it's just perfect? No buffering, no glitching? Well, that's not just luck. There's this incredible, kind of unsung hero of our wireless world called MIMO. Today, we're going to pull back the curtain and see how the simple idea of adding more antennas completely changed the game for wireless communication. Okay, so here's our roadmap for this explainer. We're going to start with the big picture, the MIMO revolution itself. Then we'll get into its two incredible superpowers, diversity and multiplexing. After that, we'll talk about a really important balancing act, a fundamental trade-off between them. We'll look at how this stuff actually works in the real world with different architectures, and then we'll wrap up by looking at why these smart antennas are so crucial for, well, everything. All right, let's start at the beginning with the revolution. To really get why MIMO was such a big deal, we first need to understand the huge problem that engineers were banging their heads against for years.
And this is the central puzzle right here. The airwaves, the radio spectrum our signals travel on, it's a limited resource. There's only so much of it to go around. It's like a highway with a fixed number of lanes. And as we all started using more devices, demanding more data for streaming and gaming, that highway got incredibly congested. So how do you get more traffic through without building a whole new highway? Well, the answer turned out to be amazing. It wasn't about finding more lanes, but about using the existing lanes in a radically smarter way. And the key? Just add more antennas.
And that leads us right to MIMO. It stands for multiple input, multiple output. Now, on the surface, the idea is pretty straightforward. You put a bunch of antennas on the thing sending the signal and a bunch of antennas on the thing receiving it. But here's what's so cool. It's not just about adding more metal. It's about using those extra antennas to unlock completely new possibilities within the wireless channel itself, giving us two fantastic new abilities. And that brings us to what I like to call the two superpowers of MIMO. You can think of them as two completely different ways to leverage the potential that those extra antennas create. You can choose to make your connection rock solid and super reliable, or you can make it ridiculously fast. Let's break down exactly how each one of these works. This slide lays out the difference perfectly. Over on the left, you've got diversity gain. Its one and only goal is reliability. The method is to combine signals to fight against all those annoying signal fades and dropped connections. The analogy is great. It's like having many voices shout the same message across a loud room to make sure it gets heard. Then on the right, you have multiplexing gain. This is all about raw speed. It works by creating parallel paths for data, essentially turning one data highway into a multi-lane superhighway. So let's talk about diversity gain. You know how wireless signals bounce off walls and furniture? Well, sometimes those reflections cancel each other out, and your signal just vanishes for a split second. That's called fading. With diversity, your device is getting multiple copies of the exact same signal, each one arriving via a slightly different path. The odds that all of those copies will be bad at the exact same moment are incredibly low. Your device can then cleverly pick the best one or combine them all to create a single, super strong, stable connection. That's why your video call doesn't freeze when you walk into the kitchen. That's diversity gain in action. All right, now for the second superpower, multiplexing gain. And honestly, this one is kind of mind-bending. Instead of sending the same information across all the antennas for reliability, multiplexing sends different streams of data from each antenna at the same time on the same frequency. It sounds like a chaotic mess, right? But the receiver uses some seriously advanced math to untangle all those signals. It's like it creates multiple, invisible, parallel pipes in the air. If you've got 4 antennas, you could potentially send 4 times the data, quadrupling your speed without needing any more of that precious spectrum. This is the secret sauce behind streaming 4K video without a hiccup. So we've got these two incredible powers, right? Maximum reliability with diversity and maximum speed with multiplexing. So the logical question is, why not just have both all the time, cranked up to 11? Well, as it usually goes in the world of engineering, there's a catch. And that catch is what we call the fundamental diversity multiplexing trade-off. The reality is you just can't have it all at the same time. You can't get the absolute best reliability and the absolute top speed simultaneously. So engineers have to make a choice. They have to decide what's more important for a specific application. If you're designing a critical medical device, for example, you're going to slide that dial all the way over to max reliability. But if you're building a system for blazing fast downloads, you're going to slide it right over to max speed. And this quote from A. Goldsmith, one of the pioneers in his field, really nails it. It's not just an on or off switch. It's not all reliability or all speed. Think of it like this. Each antenna gives you a resource you can spend. You can choose to spend some of those antenna resources on creating redundant copies of your data for rock-solid reliability, that's diversity, and then you can spend your remaining resources on sending new, unique data streams for more speed, that's multiplexing. It's this flexibility that makes MIMO so incredibly powerful.
Okay, so we've got the theory down. We understand these two powers and the trade-off between them. But how do engineers actually build systems that can do all this? Let's take a look at the real-world architectures that bring this all to life.
The main idea for boosting speed is called spatial multiplexing. A lot of the foundational work on this came out of Bell Labs with a family of architectures they called BLAST. Now, there are a couple of versions, but we're going to focus on the one that became super practical and widely used, called VBLAST. The idea is simple. Take one big stream of data, chop it up into smaller parallel streams, and send each one out of a different antenna. But the real genius isn't in the sending. It's in how the receiver manages to sort out that jumbled mess. Okay, the process on this slide is just so clever. Imagine 4 people are talking to you all at once. How could you possibly understand what any one of them is saying? Well, a VBLAST receiver does something amazing. First, it listens to that mix of signals and figures out which one is the loudest, the one with the best signal-to-noise ratio. It then focuses all its attention on decoding just that one strong signal, treating all the others as just background noise. Then comes the magic trick. It creates a perfect copy of that signal it just decoded and mathematically subtracts it from the original messy mix. Poof! The loudest voice is gone. Now it just repeats the process. It finds the next loudest voice in what's left, decodes it, subtracts it, and so on, until every single stream has been recovered. It's a brilliant process of elimination.
So far, we've really been focused on how MIMO improves the connection for a single person, for you. But the benefits of having multiple antennas, what we often call smart antennas, go way beyond just your device. They actually improve the entire wireless network for everybody. So beyond giving you more speed and a stronger signal, these smart antenna systems can actually direct the wireless energy. They can form a focused beam of signal pointed right at your device, and at the same time create nulls, or dead spots, in the direction of other people so you don't interfere with each other. This is huge. When you slash interference, the whole network gets better. A single cell tower can now handle more users, all getting faster speeds, all at the same time. That's a massive win for what we call system capacity, and it makes the entire network way more efficient. So let's bring it all home. At the end of the day, all this complicated science and engineering, the diversity gain, the multiplexing gain, those VBLAST architectures, it all adds up to the smooth, seamless wireless world we kind of take for granted now. That diversity gain, that's what gives you the stable video call that never drops. That multiplexing gain, that's what delivers a full-length movie to your tablet in just a few seconds. It really is the hidden engine that powers our modern, connected lives.
And that leaves us with a final, really exciting question to think about. We've seen the incredible leap we made going from 1 antenna to, say, 4 or 8. So what happens next? What happens when our cell towers and maybe even our devices go from having a handful of antennas to having dozens or even hundreds? This isn't science fiction, by the way. It's a technology being rolled out right now called Massive MIMO, and it's set to take all the principles we talked about today and push them to a whole new level, unlocking the next generation of wireless. And that's our look at the MIMO revolution. I really hope this helped make some of that invisible magic a little more visible. If you found this helpful, it would be awesome if you could hit that like button and subscribe so you don't miss our next explainer on the tech that's shaping our world. And we'd love to hear from you. What other complex topics, maybe something like massive MIMO or 5G beamforming, should we tackle next? Let us know down in the comments. Thanks so much for watching.